form everything you thought you knew about botulism. So as we draw out the scene, notice that we're using a lot of violet hues. That's right, gram-positive. And right off the bat, we have something for you to remember. We've used a special shape for these robots to help you remember the transmission of Clostridium botulinum. It's often transmitted by improper canning of foods. Improper or insufficient heating cycles when canning food can allow for the survival of spores, which can then germinate and flourish in the anaerobic environment, meanwhile producing loads of toxin that's relatively heat stable. And this is why we've always been told to cook canned food thoroughly. So to represent canned food, we've made our robots look like they've been made out of cans. Although it's really unlikely for them to mention home canned food directly in the stem because this would make it really obvious, they can go one logical step back and say a couple or a family are presenting with very similar symptoms, and you'll have to make the connection that they may have shared some of the same food. So be on the lookout for botulism when you hear multiple family members developing neurosymptoms. Like the rest of the Clostridia genus, Clostridium botulinum is a spore former. Our symbol for spore formers has been walnuts, but in this scene we're going to change it up a little. Since adding walnuts wouldn't make too much sense to the whole robot theme, we're going to draw mechanical nuts instead. A nice, memorable change. So the mechanical nuts stand for spore forming. As I just mentioned, the spores flourished inside a sealed can, an oxygen-free environment. This is because, like all other Clostridia, botulinum is an obligate anaerobe. We're going to help you remember this by drawing a person here on the side wearing our obligate anaerobe gas mask. So now let's jump right into the symptoms, and to do so, turn your attention to these two robots. The first thing you'll notice is that these robots are struggling to keep their bodies upright. It's like they're going limp. We did this to represent the flaccid paralysis that botulinum causes. The paralysis is obviously caused by the absence of muscle contraction. You also need to know that this flaccid paralysis is a descending paralysis, in that it starts superiorly and moves inferiorly. This is opposite from the ascending paralysis that occurs in Guillain-Barré syndrome, which we'll talk about in another video. Also remember that if it's multiple family members or maybe campers that were together that are all presenting with the same symptoms, it's probably botulism, not Guillain-Barré. This would be really unusual for multiple people to present with Guillain-Barré syndrome. Again, we'll get into that in a future video. All you need to remember now is that it's a descending paralysis. So since this means that it starts at the top, the first symptoms that may appear are eye problems, such as diplopia or ptosis. We're going to simply make these robots' eyelids droopy to help you remember their eye symptoms. Now, to really illustrate the descending nature of the paralysis, notice the robot's head is tilted over as if the neck's going limp. Then on the robot over here, he's hunched over at the shoulders. To reinforce this, we've added lights. Where the lights are on, they're still receiving power, and where it's off, they're not receiving power. And you can think of this power as nerve signaling. So now that we know it's a descending paralysis, let's talk a little bit about how the paralysis is caused. So we already began to talk about how adults got botulism. The botulinum has grown and reproduced in the sealed can and has subsequently produced toxin. This preformed toxin gets absorbed into the gut and then travels to the peripheral nervous system via the blood and causes all of the symptoms. And as a side note, it only affects the peripheral nervous system, not the central nervous system, because the toxin's unable to cross the blood-brain barrier. You'll notice that we've drawn the same character we drew for Clostridium tetani. This is because the toxin is nearly the same toxin. Specifically, it cleaves the snare protein, which prevents the fusion of the vesicles with the presynaptic nerve terminal. And all of this is identical to the mechanism of action of tetanus toxin. The only difference is the target. Botulism attacks motor neurons that release acetylcholine. Acetylcholine is an excitatory neurotransmitter, so its release causes muscle contraction. When this is inhibited, it will lead to flaccid paralysis. We're going to draw a big power supply here on the right, and instead of writing an AC current, we're going to write the ACH for acetylcholine. And the whole power supply theme will remind you that it's excitatory, like electricity is for robots. And to remind you that the mechanism of action is very similar to tetany toxin, we have this guy in a very similar suit as the guys in the tetany story, and we'll have him cutting the wires with scissors to represent that the toxin is a protease. Now we're going to talk about Clostridium botulinum infections in babies. The transmission is slightly different for babies, and examiners often write questions that rely on your knowledge of this slight difference. So let's draw out our robot baby. You can see that his power supply is also being cut by this dude, who's clearly not a fan of robots. And since he's no longer receiving the AC current or acetylcholine, he's gone limp. So the toxin's effects are the same in babies, and it causes the same flaccid paralysis, which is known as floppy baby syndrome. So the difference between babies and adults is how the baby ingests the toxin. Luckily, this is all largely intuitive, so let's understand it intuitively first, then we'll add our memory hook to help you out. As I mentioned earlier, adults only get botulism when the spores can germinate in an anaerobic environment first and produce a toxin in that environment. And the adult swallows this pre-formed toxin. The reason we adults don't get sick from ingesting spores is because Clostridium botulinum is kind of a wimp. Even though our intestines create a nice anaerobic environment for it, our normal bacteria flora outcompete it and prevent the germination of spores. In babies, however, who lack this robust flora, they have a perfect anaerobic environment without this competition. So botulinum spores can germinate and go on to produce toxin, which causes the floppiness. Now that you understand this, the only thing we need to know is how babies ingest spores in the first place. For whatever reason, botulinum spores are very commonly found in honey. In fact, they're so common that floppy baby syndrome is actually a more common manifestation of botulinum than botulism is in adults. So infants should avoid honey. To help you remember the association with honey and floppy baby syndrome, we'll draw this robot pouring honey all over the baby robot. It kind of looks like he's trying to tune him up with oil, but we've replaced the oil with honey. And it's dripping all over the floppy baby, and it's also dripping all over the mechanical nuts, which were our symbol for spores. So the spores are in the honey. So altogether, it's spores in the honey which causes floppy baby syndrome. So if you get a question about floppy baby syndrome, you better not put ingestion of preformed toxin as the answer. It's ingestion of spores. And likewise, if you get a question of how adults get the toxin, you better recall that adults are eating canned food in which the bacteria is already flourishing and producing toxin. So it's a preformed toxin. Those are perhaps the most important points, which is why I'm probably annoying you by restating it so much. So don't miss it, or I'll feel completely useless. And with that, we're done with Clostridium botulinum.